Thanks for the introduction. So my name is Zhonghong Ou, and I'm a postdoc researcher in Aalto, and today I will give a talk about the title of this talk is not so good because I will cover around maybe 2 or 3 different things, but I mean this title can cover the first part of my talk, but I couldn't find a better title to cover everything, so I just use it. So first, I will talk a little bit about the kind of M.Sc EC2 public clouds. How many of you have used? I mean, probably you have heard about it, but how many of you have used M.Sc EC2 platform before? 2. Great. Not that much. So probably it will be a little bit new to you, to some of you, but. Then secondly, I will talk something about the energy and the cost efficiency analysis of this ARM and Intel processors and comparison between different processors. Then I will talk a little bit about the kind of massive scale machine-to-machine services. I mean, we didn't have ready results yet for that project, but I just want to share what we are doing right now. And then I'm willing to get feedback, so comment regarding that work. So firstly, I will talk the performance issues of M.Sc EC2. So this is the work which I just presented 4 days or 5 days back in Boston, this hot cloud, combined with this ATC, Unix technical conference there. So cloud computing has attracted much attention from the industry, academic, and also media a lot because of very easy to use, and theoretically it has no limit, and also it can reduce the capex and the OPEX stuff, and there is something more as well. But then there is this kind of very widely and very famous public cloud provider, which is Amazon EC2. Probably you have used Amazon shopping stuff before, but maybe you have not used this EC2 stuff. So EC2 stands for this elastic compute cloud, and basically what you can do is you can rent some instances, virtual machines instances from the EC2 platform, and then pay for a certain amount of money. For instance, kind of like 15 cents per hour for an instance. So here, M.Sc EC2 provides different, actually very significant diversified instances for their services. So they have around 7 different families of instances covering standard, high CPU, high memory, micro, and the cluster, and stuff like that. And within each family, they also provide different instances according to their respective capabilities. For example, in the standard instances, they have this small, large, extra large stuff. So my talk today will mostly focus on the same instance type within the same family of instance. So I mean, since this M.Sc EC2 was introduced in the year 2006, so one could easily ask, so what would be the hardware underlying it look like? So will they use different hardware for supporting the instances, or they are using very homogeneous hardware to support their instances? And if heterogeneous hardware is used, what will be the performance like? So these are kind of the motivations of our work. There is actually some work already done in this area before, but then they have there is one Infocom paper 2010, which analyzed the kind of the performance variations among different instances. But they didn't. What they didn't do is they didn't analyze the kind of the performance variation within the same instance type. So our work actually does this work. So we use this CPU ID to collect the hardware information from the underlying platform, and also we confirmed with this CPU info to double check whether they are the same or not. And we collected information from two periods of time. One is from April to July last year, and another one is from January to March this year. We collected 200 instances for each instance types. And then I will show you a bit later this table about the hardware information. Then we also used some micro benchmark tools to verify the performance, and also kind of verify the variation of the performance of different instances. And later on, we also used some application benchmark to see how much difference the end user will be facing, because usually the end user they don't care much how big difference it is from the CPU or from the memory or from the disk, but they do care about the kind of the combined or unified combined performance variation. So we use this STT-PERF to do this work. We used around maybe 10 different micro benchmark tools, and also a bunch of application benchmark tools to verify our results and to see if the performance variation is kind of accidentally, or if it is actually true or consistent among all of the benchmark tools. So here's the kind of hardware configuration, hardware information from the underlying platform. So the left one is this M1 stands for the standard family, and this small, large, and X large means different instance types within the same family. So as you can see from this table, so even within the same instance type, for instance, this M1.small, then it uses different hardware as well. For instance, this 55/7, 56/45, and they also use different architectures as well. For instance, Intel Xeon and AMD. So this is the fact of the current public cloud platforms, and they use different hardware to support the instances and services. And what you can tell from this table is kind of the newer processor models, they are replacing the older ones progressively, as you can see from this 2012 this year. So some of the processor models which we found last year doesn't exist anymore, or we couldn't get this kind of instances type anymore this year, like this AMD 270, and also some of the 2218 actually also is kind of shrinking and decreasing in terms of the number. So this reveals kind of the trend of this hardware replacement and upgradation. So new models that are replacing the older ones progressively, and the hardware information very significant among different availability zones as well. So the availability zone here means, for instance, our institute has currently 5 different regions, or 5 or 6, even 6 right now. So within each region means you can roughly see it is kind of a data center. For instance, they have 2 data centers in the United States, and they have one in Japan, and one in Singapore, and one in Iceland. So region, you can roughly see this kind of data center. And then the availability zones means kind of a subdomain of that same data center. But it is kind of physically isolated. So if one availability zone fails, it doesn't have any influence on the other ones. So then I will show you the kind of the experiment results. So here's the CPU performance. We use this Unix bench to measure the performance. So we also used 1 and 2 instances within each instance type to do the benchmark. The reason why we did this, we used 1 and 2 different processes to do the measurements is kind of because we found from our experiments, how they use they use different scattering mechanisms as well. So for instance, in some cases, they use this SEDF, which is a short, at least left first scattering mechanisms. And then after some time, they moved or switched to this credit scattering mechanisms. And right now, they are most likely to switch from credit to credit to the credit to see a newer generation of these scattering mechanisms, and it solves some of the problems which exists in the credit scattering mechanisms before. And so here you can really see from the CPU perspective, the variation is kind of very big. If you compare this 5645 to the 5507, then you can see that the difference is around maybe 25%. And then this difference, we also found out that the variation or the difference within the same hardware is much, much smaller than among the different hardwares.
So do you think that pattern for the stars means anything?
Sorry?
Pattern for these stars, the 55430.
You mean this one?
Yeah.
Yeah, this one's kind of very, very weird one because we actually will find two different patterns. I mean, at least for instance, I mean, in some of the cases, so if you use one instance or one process, then you can allocate around 100% of the CPU processing time. But if you use two processes, then for each of the process, you can get roughly 75% of the CPU processing time. So basically means on these two, they use different scattering mechanisms for the instances. So that's also one reason why this.
So when you refer to scheduling, are you referring to process scheduling on one machine or
virtual machine scheduling?
Virtual machine.
Virtual machines, yes, kind of the hypervisor or kind of the VMM virtual machine monitoring. Yes.
So there are multiple different virtual machines running on one physical machine.
Yeah.
Not all of them under your control. Is that correct?
No, actually, we don't know. I mean, or at least we couldn't get access kind of which machine is running on which physical server or physical node.
So you're running a virtual machine, but
yes,
not
exactly.
sure there might be another virtual machine from somebody else running on the same physical machine.
Yeah, most likely there is, but we don't know. Yeah, because I mean, if you want to do this hardware consolidation, then probably they will run multiple virtual machines on the same physical machine. And because this, I mean, this is also from this kind of large instance type. So large instance has two virtual CPU, and for the physical server, it has actually 4 physical cores. So in that sense, basically, if you can get 100% for 2 processes, then one single physical server can host at least let's see, at least two. And if you get around 50% of the CPU processing time, then you can host. No, sorry, if you get 50%, then you can host around let's see, 50% for because again the Intel Xeon processors they also have this hyper thread enabled. So basically, if you have 4 physical cores, logically speaking, you can have around 8 virtual cores.
So when you sign up for a machine, are you signing up for a virtual machine?
Virtual machine.
A virtual machine.
Yes, exactly.
And it's equivalent to like 1 core. It's like equivalent to like it's supposed to be equivalent to like a 1 physical machine with 1 core.
Yeah, I can show you what the promise here. So like here, so for we use this large instance. So what they provide is kind of they said, oh, I will give you 2 virtual cores. But then you have no idea what this virtual core actually means there. So we only give you around 100% CPU time or just 50% of CPU time. So you need to do some kind of your own research work to find out that.
So they do not describe what an EC2 compute unit is.
They describe this EC2 compute units, which is kind of a one ECU equals approximately to 1 gigahertz Intel Xeon server in the year 2007, or 1.2 gigahertz AMD servers in the year 2007. So that's what they offer.
Okay.
Yes.
Are you going to describe kind of what the kind of facilities are for computation? Like that's a question. In using this facility, do you just sign up for machines and your interface is, if I sign up for 10 machines, I can send various jobs to each machine and then collect the data that each produces, as opposed to when you sign up for 10 machines, can you implement scripts or processes where the output of one machine at Amazon is passed to another machine? Do they have like shared storage space if you have 10 machines, or shared memory, or can you kind of implement a variety of kind of parallelizing environments? Do you have that available?
The answer is simply no. You couldn't. I mean, you couldn't control what kind of storage you will be using. They offer you some sort of storage capacity, but that's all they offer. So you couldn't. You couldn't know where the storage is and whether other.
For instance, if you mix two virtual machines, you can't have machine 2 access the storage for machine 1, and they can't share a virtual disk.
No.
So I think what you're saying is that you cannot be sure where the storage is located.
Exactly. Yeah.
But
The other part of
virtual.
Roy's question, I think, is can you have two machines accessing the same storage?
Right, the same virtual
And the
storage.
answer to that is yes.
Yeah, so you can set up like SQL database that have different servers.
Yeah, also the block storage.
Right.
So you disagree with these guys, or you just
So-
I asked my question in too confusing a way?
Yeah, so this virtual instance doesn't directly, without setting up different services, right? So we don't disagree with him, I think.
So the fact is, I mean, you couldn't control, I mean, the storage. So they provided you the storage, but I mean, you couldn't know where the storage is and who will get access to the storage, and furthermore, you couldn't know whether you could allocate the specific storage for yourself or not. So they provide this kind of let's say maybe 140 gigabytes storage, but then you store there. Then you don't know where is.
Hey, I don't care where it is.
Yes.
I don't care where. I mean, obviously, I don't even know where the machines are.
Yeah.
Right.
But
It's
you-
just-
So what you're saying is you cannot be sure about the exact performance of the storage, because you cannot be sure whether this is on the disk that's
Yeah.
shared with
Yeah,
some other
exactly,
user.
Yeah, so the storage, like the networking part, is kind of very tricky in the cloud platform for this RTC too, because I mean, you don't know. I mean, who is using the same services or who is sharing the same resources as you are. So, but I mean, for the kind of the CPU and then for the memory part, that they are separately located. So that's you can have some rough idea.
Yes,
some
it
rough
might
estimate.
actually, sorry to interrupt again, might actually make sense to do a little timer. Can I get a show of hands and who's familiar with what EC2 is? Amazon EC2? Okay. So it might sense to
Introduce.
introduce it a little bit at a high level, or perhaps let me try
Okay,
to.
so just imagine if you want a workstation or you want a laptop with certain capability. For instance, you have a certain amount of CPU computation capability, and you want a certain amount of memory and a certain amount disk. Then you can rent it from a virtual machine, kind of a virtual one from the Amazon EC2. That is kind of corresponding to your requirements in terms of the capacity. So I'm not sure if that helps or not.
Yeah. So I guess you can think about it from a historical perspective. If you wanted to have a server,
Yeah.
historically what you would do is you go to Dell or somebody, buy a server, put it into your lab, install an operating system and run it. And at some point you will realize that the service you're providing is so successful that the server is not powerful enough anymore. You need another server. So you again go to Dell, buy another server, put it next to the server in your lab, and so on. And at some point you will notice that the disk is failing the first server, so you replace that and you would upgrade the server, and at some point your space is too small, so you get a bigger building, and so on. Then things went to these sort of hosting facilities where instead of putting these servers into your lab, you would buy them and put them into somebody else's facility that has a much better internet connection and all the cooling requirements and so on. And now these days, what Amazon has, perhaps as one of the first ones, has started providing, is that you don't need to worry about all these details anymore. You can just go on Amazon's web page, and by clicking a few buttons, they give you a server, one of their servers. And you can get a complete Unix interface to them. You can SSH into that server. You can log into that server. You can install any software you like and run the thing. And if the disk fails in the server or anything else breaks in that server, they will just move all your data and your computation to a different server without you ever noticing. So they take care of all the maintenance that's related to that. And if you run out of, if your server ever gets too small, not powerful enough to handle all your computation, with one more click of a button, they give you a second server and a third server. And to some extent, it seems nearly unlimited in the number of servers they can give you. So many of these internet startups find that very attractive because where these days internet startups are all about advertising dollars, and advertising is all about getting as many people to look at your web page as possible. And you never want to get stuck in this situation where suddenly your service gets extremely popular, but you don't have enough server capacity to handle it. And so many of these startups are building on these Amazon cloud services or other similar service providers these days. Because if they, with a click of a few buttons and by entering your credit card number, you can increase the server capacity you have, almost unlimited. And if you ever happen to hit the news and get a lot of traffic at one point, you can easily accommodate that. So you can think of these as sort of virtual servers where your server is in a virtual machine that can be moved around to any physical server. They have data centers across the world, so you can select and pick a little bit from which locations you would like to have service, but you don't have fine-grained control about where within a data center the server actually ends up, on which disk in that data center your storage is actually located. Perhaps that's some sort of high-level summary of what they provide. In addition to that, they have a lot of software services, so if you don't just want a basic Unix login, but you want an SQL database, another click of a button will give you that. And there's a bunch of other kind of software tools that they provide.
Yeah, that's a great explanation.
So what do these servers cost? Just you mentioned
15 cents an hour. That's one example. So there's a pricing is by compute time, by storage usage.
So here's the price list of
by internet bandwidth usage, and these are, I think, the compute time.
I think Amazon is what Amazon Institute offers you right now is kind of a fixed amount per hour. So if you run one instance for 1 hour, then you pay for this more, you will pay 8 cents. If you rent this medium, it is 16 cents, and then it is large, it is 32, and if it is extra large, then it's 64 here for the standard.
And this is per actual read hour of actual usage.
Right. So you can turn your own server on and off. It's for the amount of time that your server is on.
Suppose would you use these as web servers if you wanted to?
Yes,
That's what most people do, yes.
And when you use them as web servers, suppose no one accesses your web service because it's not popular. You end up paying less?
Yes, you still have to pay. Yeah, this is the charging model of pharmacies too. But in some cases, in Google and Google Engine, then they charge you for the CPU cycles. But here, they charge you for the kind of the fixed amount of hours which are using the service.
So here it's like, oh, if your web server is up, it's always whatever it is, 11
So there's
cents per hour, whether anyone accesses it or not.
Right.
So there's several different charges involved. You said the compute charges, and just to be able to respond to a web request quickly, you probably want to keep at least one server running all the time. So you will be incurring compute charges for that one server. But you could think, if you were a very large web provider, you could think about adjusting the number of servers you keep running based on your load predictions or current load that you're paying. And in that sense, you will get a much more load adaptive charge. Or just that when you scale down to that last server, that you probably always want to keep running. The other big portion of your charges will be your bandwidth cost, and that is load adaptive by nature, because if you're not generating any traffic to your server, you're not incurring any bandwidth cost. But since Amazon operates at such a large scale, their costs tend to be quite low compared to running your own server in the lab, or at least to running your own server in your house. You have to think about the energy costs, about the air conditioning cost in the summer, about the cost to swap out the disk when it breaks.
But somehow you're looking at $2 a day and $700 a year.
Yeah.
$2 a day and $700 a year.
Yes.
I guess what you're saying is, oh, you think about, there's fixed costs and marginal costs. So,
right. And there's a lot of maintenance costs that most people neglect.
Right.
Because 2 years down the road, somebody will have to spend the time to run a new server from down, migrate all the software to this new server, and $100 an hour for a skilled person. That's a dramatic cost.
interesting, right?
Okay.
Windows is like 50% more cost than Linux.
That's because Microsoft takes its share of it.
Yeah. So so this is the kind of the memory results. I mean, here in the game, then you really tell the difference between different processor models. For the 15645, it is still performing much way better than the 5507 because I mean they use different CPU clock speed, and then they also get different CPU usage. I mean CPU processing time from the same physical server. So what I just want to show here is kind of from the CPU, memory, and disk. I mean the difference. They are also very significant. And then for this, so this is kind of the application level performance benchmark. So we use this STD perf to do the measurements. So basically what this benchmark tool does is kind of you send a request, and then the server will send you back responses. And what we do with this kind of request and responses, we do some sort of dynamic calculation. Once the server gets the request from the client, then the server will do some sort of calculation or summation from 1 until 100, do some sort of mathematical summation, and then send the response back. So it is kind of like a CPU bond, and also kind of network bond, or maybe some of the memory is also has been highly used there. So here you can see from the application level, and this level is kind of any user really cares about, because I mean this is where the difference. But what the difference is really for them. So here the kind of the difference from the different components of the server, from CPU, memory, and disk, and they can be integrated and expanded here. So previously you will find the difference is around maybe 25% or 30%, but here you can really find the difference is around 60%. So here for the end users, I mean basically it means like if you're lucky, then you can have two instances. Or if you're not lucky, you get that kind of slow instances, then you have to pay for 3 instances. for the same amount of performance to HTTP requests which you want to serve. So then, I mean, from the user's perspective, this is not fair, because if I pay for the same amount of money, if I pay for 60 cents for the same instance, then I'm supposed to get more or less the same performance from the Mammoth Institute platform, but this is not the real life like. So then we developed some sort of very small and simple mechanism to how to actually optimize your instances. We use this kind of like trial and failure methods. So you can apply for some instances, and then you can have some tests on it. And if the instance is performing well, if it is fast, then you keep it. Otherwise, you just drop it and then apply for some new ones. Very simple trick here. But then you can really see, I mean, use this kind of trial and failure methods, you can actually achieve very much cost saving. So here is kind of the cost analysis graph here, and then let's imagine two different instances are co-located in the same instance type. So one is fast one and one is slow one. So if 90% of the instances they are fast ones, so this kind of trick doesn't happen much, because I mean, by nature, then you will get a very fast one, but at least at the probability of 10%, you will get this fast process. But if the fast and the slow instances, they are kind of equal, kind of like 50 to 50. Meaning that, I mean, half of the instances they're fast and half they're slow. Then if the fast is kind of 2 times faster than the slow one, then the cost saving you will get is around 25%. So basically means like if you're running a certain number of instances for a whole year, then you will save around 25% of the money which you will pay normally. And then if we move on, if the kind of the fast instance is very few, is very few, if it accounts for very little proportion of the overall instance types, then you can seek for the fast ones, and then you will get around maybe 42 or 45% of cost saving. But then here is the precondition is kind of like you want to run the instances for a decent long period of time, because I mean, with this kind of select and drop, then you will also cost you. Like if you select one instance and you drop it, then how much is true? We'll charge you anyway for 1 hour. So if we did some calculation here, like if we run the work or the instances more than 38 hours, then it will be more beneficial to use this kind of trial and failure mode. But if it is less than 38 hours, then you better keep your luck, kind of like to accept what Mammoth Institute offers you naturally.
So these results are all based on CPU benchmarking?
Benchmark the HTTP curve application level. Yes, exactly, yes. So the conclusion of this kind of very simple work for workshop paper, and then the conclusion is kind of obvious too. The actually uses very diversified hardware to host the same type of instance, and based on this kind of diversity, the performance also varies a lot. And then in general, the variation between the fast instances and the small one and the slow ones, they can reach up to 40%. But I mean, if it is put in the application level, it is enlarged to around maybe 60%. So so by using the kind of the trial and failure trick here, so you can get some benefits, kind of cost savings.
So you were running HTTP directly on the VM, right?
Yes, exactly.
Or you were generating your requests over a network today?
No, we are running actually for both client and server in the Commons is in cloud, because we want to get rid of the kind of the bottleneck of the network. If you're running the HTTP clients locally, then you will be facing the throughput, or you might face the throughput bottleneck in between the client and the server in Mammoth Institute. So that's why we choose to run it directly on Mammoth Institute. So right now we are investigating the kind of the scattering mechanisms, because like I said before, M.Sc actually use different scattering mechanisms to schedule the VMs, and right now we are trying to analyze kind of the performance variations from the scattering mechanisms as well. Actually, we have done this already. And also, we are trying to build some sort of a homogeneous platform from the heterogeneous hardware, considering the kind of the processor, variation, memory, disk, networking stuff. So this is kind of work which we are doing right now, and so this concludes the first part of my talk. And then I think I have to run a bit quick.
30 minutes.
Yeah, for the second part. So the second part is kind of analyze the energy cost of different processors. Specifically, we analyzed the ARM and the Intel processors, like in terms of the performance and also the costs. So this is a paper here which was presented 1 month back in this 6th grade 2012. And so the motivation of this work is kind of the current theory. The data centers they use kind of they switched from the scale up strategy to the scale up strategy. So scale up means kind of you use like a high performance computers, kind of like you integrate more and more processors on the same die. And then scale out means that you can use commodity servers, but you use bigger number of the servers. So right now, this kind of scale up to scale out shift has been happening in the data center world, and in the embedded systems world, then the battery is kind of is a inherent consideration, and the performance is increasing dramatically. Actually, ARM has, HPS has announced some sort of events which they use ARM processors to build servers. Nowadays, and I contacted them, and then they replied me that by the end of this year they will have some sort of servers out by the end of this year. And then, so what if these two worlds, their approach? They kind of like they move towards each other. So that is kind of the motivation of our work. Like if we want to analyze if it is possible to build some server from the ARM processors, and also kind of like what are the kind of performance you will be facing if you are using the ARM processor to build the server, and will you achieve benefits from the kind of energy consumption. So we analyzed two different platforms. One is this Intel Core 2 Q9400, and they were also used for panel boards. Panel boards is kind of ARM-based development boards, and it has dual core 1 GHz CPU models. So we build a cluster which consists of 4 panel boards, and we compile this ARM-based cluster to the Intel server, and then try to see their differences in terms of the performance and in terms of their energy consumption. So we use this EE. EE means like energy efficiency index, which you can see kind of work divided by energy, or kind of performance divided by the power. So here's the detailed configurations. I will not go into the details of these configurations, but basically the principle is kind of we try to use more or less same configurations for both of the configuration for both of the platforms. But here is the difference. So the storage, the panel board and the Core processor, they use different storage. So we try to avoid the applications which involves the hard disk. And then here is also the network difference. So the panel board has 400 megabits per second Ethernet, but then the Intel workstation has 1,000 megabits per second Ethernet. So we like before, we used different tools to measure the performance. We measured three different aspects of the performance. One is web server throughput, and one is in-memory databases, and a third one is video transcoding. So here are the results for the kind of the three different applications. So this one is for the web server throughput, and here you can see the difference between the ARM processors and the Intel processors is kind of around one. So in terms of energy efficiency, the ARM processors, they are more energy efficient. It is around 1.6 times more energy efficient than the Intel servers. And then for the same level of performance, then you need more ARM processors to be comparable to the Intel processors. That's not surprising. And then for the dynamic one, actually you can see the performance level, or kind of the energy efficiency index, increases when the CPU usage is increasing. Basically, it means that if you want to achieve a better energy efficiency, you better to keep the processors busy and kind of close to its peak point, or kind of maximum capacity. But then at some phase, there is some kind of interesting phase here, which is kind of flat. I mean the energy efficiency index does not increase as the CPU usage level increases. So we dig into this, and we found out, actually the Intel processors, they use kind of speed step, this kind of dynamic voltage and frequency scaling stuff, DVFS stuff, and when the server is at a low load, then it will decrease the frequency of the processor. But if the processor is kind of is processing a high load, then it will increase the frequency of the processor and also keep more cores busy. So here you can see the power consumption of this. So if we disable the speed step, then the curves, they are kind of very flat. But if you have this speed step enabled, then you have this kind of very nice curve here, kind of gap around the CPU usage level, 30% to 40%. So here is the energy efficiency comparison of the two processors in the same CPU utilization level. So basically means like if you have the ARM processors CPU busy as 40%, and if you keep the Intel processor busy at 40%, then what is kind of the energy efficiency difference? So here you can see when the ARM processors and Intel processors, they are at the same level of CPU usage level, then the energy efficiency difference is not that big. It's around 1.2 times.
What is low, medium, high?
Low, medium, and high is kind of the web server throughput stuff. So low means kind of we do the calculation from 1 to 100. And medium, we do the calculation from 1 to 1000. And the high, we do the summation from 1 until 10,000.
Request.
So the dynamic web server request means when the server receives a request from the client, it will do some mathematical summation, and then we return the result of this summation to the client. So the low, medium, and high means like the summation is from 1 to 100, from 1 to 1000, or from 1 to 10,000.
I see.
Yeah. So here's the in-memory databases kind of network tools for the performance comparison. So probably you will not want to see the kind of the power and the times, but then for the energy efficiency ratios, then for the full table scan, then the difference is around 9.5 times difference. So it's kind of huge. So basically means for the same amount of work, the ARM processors the Intel processors, they will spend around 9.5 times more power on the same work. And for the update and insert and delete, it is around 2.6 to 3 times. So for the in-memory databases applications, the difference is actually very big. And here's the video transcoding. Here, I mean, the result is not that big because for the video transcoding, it needs the computation of the CPU much, and the ARM processors, they are not that good as the high intensive computation jobs or works. So the difference here is around 1.2 or something. So here's the kind of summary of the differences among the two different processors. So for the web server, it is around 1.3, and for the email databases, it's around 2.6 to 9.5, and for the video transcoding, it is around 1.2. But then for the same amount of work, then you will need more ARM processors to be comparable to the Intel processors. For the web server, you need 12. For the in-memory databases, you need maybe 1.3 to 4. Or for the video transcoding, you actually need 16 processors to do the same job. So we also analyze the cost to see to all.
So you're saying that even though you're using 12 or 16 processors, it's still more power efficient?
Yeah.
Fewer processors.
Yeah, sure. Because I mean the energy efficiency index doesn't change whether you use more or not. Because we use kind of the power divided by the so we use the work done by the energy, and also kind of like the performance divided by the power. But then again, if you are using more processors, then you need to spend more money on purchasing this kind of these processors. So here is kind of the cost efficiency analysis of the.
And you're assuming that you have a workload that you can parallelize with minimal overhead.
Yeah, exactly. Yes, that's
You would have to account for this.
yeah, that's actually a very good point, because I mean that is not our finding, but kind of consensus that I mean the embarrassingly parallel workload is, I mean they're just for this kind of like maybe web like HTTP requests and stuff like that. So they are not that good for the kind of tasks or jobs. They are highly dependent on each other. So you couldn't do it in a parallel way. So this kind of workload for this kind of ARM processors, they are good for the parallel tasks. So here, I want to go into the detail of the analysis of the cost, but I mean the basic message or the basic takeaway message from this figure is kind of the ARM processors. Even though you have to spend around maybe in the video transcoding case, you have to use 16 ARM processors to be comparable to a single Intel processor. Still, the cost is not. I mean, using the ARM processors, they are kind of still more cost efficient than the Intel server. Because let's imagine, for instance, for Intel server, for Intel processor, for this 5645, it is around $500, but for ARM processors, something like $50 or $20. So the price difference is also very huge. I will skip this one for you. So the basic conclusion is kind of the two take-away message from this analysis. Kind of the ARM processors, they are in general they are more energy efficient than the Intel processors. But the variation can be from 1.2 times to 9.5 times. But then the ARM processors, they are more beneficial for the lightweight load. rather than the computation intensive node. So if the workloads they are more and more computation intensive, then the benefits you can achieve from the ARM processors is decreasing very significantly. So probably you will not use this use the ARM processor for doing this kind of job or tasks. But so this is kind of the future work which are actually we have covered this Intel Atom processors can be seen between the ARM processor and the Intel Core 2 processor. And then probably I have some time to talk a bit about the project. I will give very brief introduction of the work which we are doing right now. This kind of it is called a Mammoth Project. It's a massive scale machine-to-machine services, and basically the core idea, the motivation behind this this massive scale machine-to-machine services is kind of the core of internet. Consists of maybe millions of nodes, and then the edge of the fringe of the internet you contains billions of nodes. Then maybe for the Internet of Things scenario, then probably you will be facing like trillions of nodes. So so with this huge number of nodes, if you want to do some sort of deploy some kind of sensor networks, or kind of deploy some applications for the Internet of Things, then you want to have some sort of experiments beforehand or before you actually deploy the services. So our work is kind of doing this kind of emulation or doing this kind of experiments before you deploy your resources. So we plan to build this very large scale kind of scale up to 10 millions of nodes by using this CoAP protocol. CoAP protocol is a constraint application protocol which is defined or standardized in the core constraint RESTful environment LTF working group. I'm not sure if you have heard about it before, but I mean this is kind of constraint. I mean this kind of HTTP-like protocol specified for the constraint devices like sensors and the sunspot stuff. So we will build this large-scale emulation platforms specifically for the constraint devices, and then we will trying to analyze or try to understand the problems of building this kind of large-scale emulation platforms. Kind of, for instance, you will be short of ports, and you will be short of memory, and then you will be facing kind of like if you use different secure path. So for instance, if you use this M.Sc or if you're using this DTR stuff, then probably you will be facing different problems as well. So we are trying to understand all of these problems by building this kind of platform, and then we will also do some sort of congestion control and group communications in this large-scale emulation platform. So that's basically what we will be doing in this project. This project has been running for around 1 year, and we have this platform. Right now we have this platform can be running up to tens of thousands of nodes. Then later on we will extend it to run even larger or bigger number of nodes. So that's concludes my talk today. So you're welcome to have any questions or comments.
Thanks, speaker.